big enough for people to see?
I think so.
Okay. All right.
Okay, so then maybe we can start. So we have today Gabriel Frieden. I think that's how it's pronounced. From Montreal. And
yeah. Okay. Yeah. Well, thank you, Matteo, for inviting me to speak in the seminar. Well, I guess so. I'm a combinatorialist, and I've given the version of this talk to combinatorial audiences before, but I'm kind of excited to give it to a probabilistic audience. But so please feel free to interrupt me and ask questions, ask for clarifications if I sort of maybe if I rush past something that maybe I think is that might be. Yeah, I don't know exactly what is sort of familiar to people in your community versus I know better what sort of the people that I usually talk to in combinatorics are familiar with. So please feel free to stop me if you want clarification on something. Okay, so yeah, so I'm going to discuss this joint work with Florian Egner, who's also a postdoc in Montreal. So, okay, right. So let me get started. So I want to kind of introduce the main topics of the talk, sort of with this view towards different ways of sampling the Plancherel measure. So, so I'll just start with some notation. So a partition is a weakly decreasing sequence of non-negative integers, like this here. And typically we represent a partition by its Young diagram, which is where we just put, so we put the first part, we put that number of boxes in the first row, then we put the second part, 6, we put 6 boxes in the next row, 3, 2, 1, 1. So this is a very convenient representation of a partition. And we say that the sum of the parts, or the number of boxes in the Young diagram, is called the size of the partition, and we denote it with this absolute value sign. So this partition has size 20. Okay, so we're going to need a few definitions related to the cells of the partition. So if I take a cell C, or a box, then its arm consists of the cells that are to the right of it, and its leg consists of the cells that are above it. And then the arm length is the number of these cells, and the leg length is the number of these cells. So the arm length is 5, and the leg length is 3 in this case. And then maybe a more familiar quantity is the hook length, which is the arm plus the leg plus 1 for the cell itself. So that's the hook length of the cell. And this quantity h lambda, which I'm going to define as the product of all of the hook lengths, this is a very important quantity that will show up throughout the talk. Okay, so now a semi-standard Young tableau, or SSYT, of shape lambda is a filling of the cells of the Young diagram with positive integers so that the rows weakly increase and the columns strictly increase. In particular, a standard Young tableau is a semi-standard tableau where each of the numbers 1 up to the size of the partition appears exactly once. So, for example, if I take the partition 3, 2, then there are 5 standard Young tableau, which look like this. These 5 tableaux here. So I'm going to write f lambda for the number of standard Young tableau of shape lambda. That's sort of the traditional notation for it. And so then there's this amazing hook length formula, which says that this number of standard Young tableau can be computed by this product formula. So you take the size of the partition factorial divided by the product of all of its hook lengths. So if you want, you can check this for the shape 3, 2. So you'd have to figure out what the 5 hook lengths are of each cell, and then you do 5 factorial over that number, and you should end up with 5. So it's kind of an amazing formula, and it's very useful in probability, as I'm sure most of you know better than I do. So maybe I'll say a little bit more about that later, but okay, so, right, okay, so now another kind of central thing having to do with Tableau are Schur functions and the Cauchy identity. So the Schur function is, well, there's different ways of defining it, but I'm going to take this as the definition, where I take all of the semi-standard Young tableau of shape lambda, and then for each tableau I associate a monomial, where I just do x1 to the number of times 1 appears, x2 to the number of times 2 appears, etc. And I take an infinite set of variables. So one of the fundamental properties of the Schur functions is this Cauchy identity, which tells me that if I take this sort of simple product in 2 sets of variables x and y, this is expressed as the sum over all partitions of the Schur functions in x times the Schur functions in y. So now, so the Cauchy identity, this is sort of has all sorts of applications in representation theory, probability. But the part of it that I'm going to be focusing on in this talk is what happens if you take a specific coefficient. So if you look at the coefficient of this monomial x1 through xn, y1 through yn. So if you look at the right-hand side, well, you get a monomial like that if you have a tableau, if you have a pair of tableaux where each number just appears exactly once. So that's precisely the number of standard Young tableau of shape lambda. And then on the right-hand side, it's not too hard to see that the coefficient of this monomial is just corresponds to permutations. So there's n factorial of them. So this is a very classical identity that goes back to Alfred Young, I believe, in his study of representations of the symmetric group. So one immediate consequence of this identity is that if I take the ratio f lambda squared over n factorial, this defines a probability measure on the set of partitions of size n. And this is the Plancherel measure. So, okay, so now what I want to talk about is a couple different ways that one could sample from the Plancherel measure. Okay, so the Robinson Schensted correspondence is a bijection between permutations and pairs of standard Young tableau of the same shape. So if we go back to this identity, so Robinson Schensted gives a combinatorial proof that the number of permutations is equal to the number of pairs of tableau of the same shape. So and another way to think about it is that if you choose a permutation uniformly at random, the pair of tableau that you get will have shape lambda with probability equal to this Plancherel measure, because the number of pairs of tableau of shape lambda is f lambda squared. So now let me give an example of how this algorithm works. So I start with a permutation. Say this permutation in S6. So I'm using one line notation. So this means 1 is sent to 5, 2 is sent to 2, 3 is sent to 6, etc. So here's how I compute a pair of tableaux. So I start with the empty tableau with no boxes. Then I take the first entry in the permutation and I stick it into the tableau. Oops. Then I take the second entry in the permutation and I try to add it to the first row, but I can't put the 2 next to the 5 because that would violate the strict increasing condition of standard tableau. So instead I have to bump the 5 out of the first row and it moves up to the second row and I end up with this. Okay, so next the 6 comes along and the 6 can just sit at the end of the first row next to the 2. Now the 1 comes along, the 1 is going to displace the 2 because it's smaller than 2. the 2 is going to move up to the next row and bump the 5, and the 5 is going to move up to the third row, resulting in this. Okay, when I insert the 3 is going to bump the 6. So 3 is happy to sit next to the 1, but it needs to bump the 6. And then the 6 moves up to sit next to the 2. And then finally, the 4 just comes and happily sits at the end of the first row. So in this way, I produce one standard tableau with n boxes in it. So where does the other tableau come from? Well, what I can do is I can view the order in which cells were added in this procedure. And that's what the q tableau is. So the first cell that was added was, well, it was just this cell. Then the next cell was above that one. The third cell added was to the right, etc. So by recording the way that this p tableau grew, I get another standard tableau. And it turns out that the information of this q tableau is sort of exactly what you need to be able to reverse the procedure of constructing p. So you do, in fact, get a bijection. Okay, so any questions so far? Okay, and I guess I should say, so I know that this idea of kind of taking a permutation. Well, let me just say, so one property, and I apologize if I'm sort of saying things about probability that all of you, well, first of all, if I say something that's incorrect, but also if I just say things that you've all known for a long time, but I just want to try to emphasize connections with probability when I can. So there's this famous problem of trying to understand the distribution of the longest increasing subsequence in a permutation, and this map is one of the key tools used to solve that problem. So the idea is that the longest increasing subsequence of a permutation corresponds to the length of the first row under Robinson Schensted. So the way that distribution was analyzed was basically to it basically has to do with this Plancherel measure, and it is the key to analyzing it is sort of the fact that you have this very explicit formula for the number of standard tableau, basically the hook length formula. So okay, so this is a really fundamental map in all sorts of areas: algebraic geometry, representation theory, combinatorics, probability. Okay, now this is maybe a bit less familiar, but this is another beautiful way to sample from the Plancherel measure. So the way this works is, so this is, I'm going to call this the exterior hook walk. So the exterior hook walk is a step for growing, for adding a box to a Young diagram in a random way, and if you apply it repeatedly, you'll sample from the Plancherel measure, as we'll see. So what you do is you start with the Young diagram of shape lambda, and then you start with a box far away. So far away is just going to mean that it has to be beyond, it has to be to the right of this last column and above this top row. That's as long as it's sort of in this spot or up from there, then it's okay. So then what I do is I look at the boxes in what I'll call the exterior arm and the exterior leg of the cell. And I'm just going to choose one of these red boxes uniformly at random and move to it. So maybe I move there. Okay, so now I do the same thing. I look at the exterior arm and the exterior leg, and uniformly at random, I choose one box to move into. And I just keep doing this until I can't do it anymore, which means that I've ended up in an outer corner of the partition. So I've ended up in a box whose addition to the partition produces a partition. And so I'm gonna call this new partition with this extra box new. So the outer corner is represented by the skew shape new minus lambda. Okay, so I start with a box far away and I just do this procedure until I hit one of the outer corners. Now, the theorem is that as long as the box starts far enough away, then the probability that it ends up in a specific outer corner is given by the ratio of the hook lengths of lambda to the hook lengths of the bigger partition nu. So that's not at all obvious from the definition. It's a very nice result of Greene Nijenhuis Wilf.
Can I ask a question?
Yeah.
Does not depend on the starting point of the box? Like,
yeah, that's right. So as long as you start in a position where you have access to all of the outer corners, you get the same probability.
I see.
If I were to start somewhere like here, or here, say I don't have access to this outer corner anymore, so then it's a slightly different probability.
I see.
Yeah. But yeah, this is kind of this sort of has this surprising property that kind of as you're doing the random walk, it's sort of like the probabilities don't change until you move somewhere that eliminates one of your options. So once I move past this column and I no longer have access to this box, now my probabilities change. But otherwise, kind of, if I just move one square over, like nothing happens right away with the probabilities. Okay, so now, well, if I start with the empty tableau and apply this procedure n times to add n boxes randomly, if I just keep multiplying these ratios, what I end up with is h of the empty tableau over h of the final shape. And h of the empty tableau is just 1. So I get 1 over h lambda, which is equal by the hook length formula to f lambda over n factorial. So right, so the probability that any specific tableau of shape lambda appears is this. And then since there's f lambda possibilities for a tableau of shape lambda, the shape lambda, if I just care about the shape and not sort of the way it grew, I get the Plancherel measure as the probability. So, right, so we have two very different kind of classical ways of sampling partitions with this measure. One is we randomly choose a permutation and we do the Robinson Schensted insertion and see what shape we get. Another is we start with the empty tableau and kind of randomly add boxes to it. So it's sort of like the Robinson Schensted is kind of, it's a deterministic algorithm, and we just sort of randomize the input, whereas this is just a fundamentally random process. Okay. So any other questions before I move on?
So I have a question, probably related to the comment by Sayan. Do you have an argument why? So for example, if you start the box like just one box above one at the height, which is one cell, one coordinate above the longest column, but very, very, very far to the right. So how is it possible that
so if I start like way over here.
Yeah, but just above the tableau.
Yeah. So
is there an argument?
The idea, right? So I guess you would think that in this case it's more likely that it would end up here, maybe. Is that?
Yeah, intuitively.
Yeah. So so why does it not work like that? So
I mean, aren't there many more cells in the horizontal leg? So it's more
Yeah.
likely that you'll just travel horizontally than travel
Yeah,
down.
I mean, I think that's, yeah, that's kind of the way
Interesting.
to think about it, I think. Yeah, yeah. The chance, if you're way over here, the chance of moving down is very small compared to the chance of moving across.
Okay. Thanks.
Yeah, thank you. Is there, who made that comment?
That was me.
What's your name?
Roger. Oh yeah,
Okay,
sorry, maybe you
well,
can't see my video.
well, thank you, Roger.
Thank you.
Oh, and maybe I should say that there's actually another version of the hook walk where you randomly choose a box inside the partition and move it out as far as you can. And that hook walk actually allows you to prove the hook length formula. So this exterior hook walk, which appeared a few years later, so it's the same authors, but then a few years later, they put another paper out with this exterior version, which proves the Cauchy identity, the f lambda squared equals n factorial identity. Okay, so right. Okay, so now I want to generalize from Schur polynomials to Macdonald polynomials. So the Macdonald symmetric functions are a basis of symmetric functions in two additional parameters, q and t, which were introduced by Macdonald. And so one of the reasons why people like Macdonald polynomials is because they specialize to lots of other families of symmetric functions. So if I set q and t equal to each other, I get back the Schur functions. If I set q equals 0, I get the Hall-Littlewood functions. If I set t equals 0, I get the q-Whittaker functions. And I can also get these Jack symmetric functions by doing this, t equals q to the alpha, and then sending that q to 1. So kind of the fact that all of these different families of symmetric functions could be united as common specializations or degenerations of one sort of master family of symmetric functions is kind of what's nice about the Macdonald polynomials. So the p lambda together with the dual, so the p lambda are defined by specifying a certain inner product, and the dual basis with respect to that inner product is denoted q lambda, and together these two families of symmetric functions satisfy this generalization of the Cauchy identity. So the right-hand side looks just like the right-hand side of the Cauchy identity, but now the left-hand side is more complicated. So you can see that if I kill t and q, then I'm just left with 1 over 1 minus xi yj. But in general, it looks like this. And this identity is the starting point of Borden and Corwin's theory of Macdonald processes. Okay, so now sort of from my perspective, kind of the viewpoint that I want to take is that there are these explicit combinatorial formulas for p lambda and q lambda. So they're defined abstractly in terms of this inner product. You say it's the unique basis which is orthogonal with respect to this inner product and upper triangular with respect to the monomial symmetric functions or something like that. But there are these explicit combinatorial formulas where you sum over the semi-standard tableau, and then you put in for each tableau a certain rational function as its weight. So I'm not going to give a precise definition of these rational functions because it's a little bit involved and it's not so necessary for the talk. But I will just say that I'll give an example here. So if I take the Macdonald polynomials corresponding to the partition 2, the coefficients look like this. So in general, they're always going to be products. They're always going to just consist of things that look like 1 minus q to the something, t to the something. And you get products of things like that divided by products of things like that. They always have the property that if you set q and t equal to each other, then all of these factors just cancel out and you get back to the Schur functions. Okay, so right. So now if you look at that generalized Cauchy identity and do the same thing we did before, which is take the coefficient of this particular monomial, then on the right-hand side, we get the sum over standard tableau again. But now instead of just having, so in the Schur case, we just had a weight of 1 for each pair of tableau. But now we have this more complicated rational function weight. On the other hand, the left-hand side is going to end up again being a sum over permutations. And the only difference is that we end up having to weight each permutation by this 1 minus t to the n over 1 minus q to the n. So I get this identity by taking that coefficient. And it's just sort of more natural, I guess, to move this factor here to the other side. So I'm going to rewrite it like that. Okay, so I guess our starting point for this project was basically looking at this identity and wondering if we could prove this directly from the definition of these rational functions rather than deducing it from the Cauchy identity. Yeah, and the idea behind this is that so the Cauchy, in the case of the Cauchy identity, originally the Schur functions were defined as determinants, and the Cauchy identity was sort of proved using determinants. But when you try to prove the Cauchy identity combinatorially, it leads you to this Robinson Schensted algorithm, which is a very interesting thing and has lots of applications. So we thought, okay, well, maybe if we can kind of mimic that for this generalized identity, maybe we'll come up with an interesting combinatorial algorithm. Okay, but we run into an immediate problem, which is that if we write down what the two sides look like in the simplest case, n equals 2, well, what the identity is saying is that 1 plus 1, the number of permutations, is equal to the sum of these two rational functions. So, well, that's quite a bit more complicated than the situation for Schur functions. So for Schur functions, it would just say 1 plus 1 equals 1 plus 1, and then we can try to define a bijection. But here, I can't just say map this permutation to this pair of tableau and this permutation to this pair of tableau. That's not going to prove this identity. So we have to introduce the idea of a randomized insertion algorithm. So here's what we can do. So I want to kind of understand why does this identity hold? So I mean, you could check that it works in maybe 30 seconds or something, but I kind of want to be able to understand this for higher values of n, where there's going to be way more terms on each side. So here's one way to understand this. So I'm going to assign a probability, or I guess maybe I should say a probability, because it actually depends on q and t. So I say that the probability that this permutation maps to this pair is 1 minus t over 1 minus qt. And the probability that it maps to this pair is, well, just 1 minus that. So you can check that this plus this equals 1. And similarly, I define probabilities that this permutation goes to those two pairs. And the point is that if I look now at the probability that I hit this pair, say, well, it's going to be 1 times this probability of going down plus 1 times this probability of going across. And that sort of clearly is equal. So this is sort of an easier identity than this. I would slightly easier. And similarly, the probability that you hit this pair is the sum of these two. And you can check that it works out. So okay, so kind of the goal is to be able to come up with probability. Our goal was to come up with probabilities like this for general n. So you have the whole list of n factorial permutations and the list of n factorial pairs of tableau, and we want to come up with probabilities that will allow us to see why y, the n factorial, is equal to the sum of all of these complicated weights. So I'll explain. I'll say a bit more about these weights and kind of I'll explain, well, somewhat where they come from in the course of the talk. But maybe one thing I should point out at this point is that these weights have some nice properties. So one property is that if q and t are between 0 and 1, then these are actual probabilities because all of the quantities are positive. In addition, if q and t are both greater than 1, then both of these, since there's the same number of terms in the numerator and denominator, the ratio will again be positive. So I get actual probabilities if I take q and t to be greater than 1 also. That's so you can also say, so what basically I can do this thing where I replace q and t with q inverse and t inverse. And if I do that transformation over here, it turns out that the weights don't change. They're invariant under q inverse, under q goes to q inverse and t goes to t inverse. But these probabilities do change. So I can get kind of another sort of nice choice of probabilities by doing that inverting of the parameters. And maybe one other thing I should point out is if you set q and t both to 0, what happens is that this becomes 1 and this becomes 1. So you recover the Robinson Schensted bijection. Okay, so right, so here's this more general framework of so I suppose I have two weighted sets, and I want to show that the sum of the weights over one set is equal to the sum of the weights over the other set. So in our case, the sum on the set on the left is permutations that are each weighted by 1, and the right hand side is the sum of permutations each. Sorry, the sum of is the set of pairs of tableaux each weighted by this complicated weight. So one way to prove this identity is to find probabilities of mapping from something on the left set to something on the right set, such that for each y in the second set, the weight of y is equal to the weighted sum over the probabilities of reaching y from x. So here probabilities just means that these things sum to 1. So they can live in any ring. They don't have to be positive real numbers or anything like that. And of course, if you have expressions p of x to y that satisfy this and also satisfy this, then just by summing over y, you immediately see this identity. And so we call a collection of probabilities a probabilistic bijection from the weighted set x to the weighted set y. And so I originally, so that like the first place I heard of this idea was I was at a talk by Alexei Bufatov, who was talking about a randomized RSK algorithm for the Hall-Littlewood polynomials. So I heard that talk and I thought it kind of seemed like a cool idea. And then also there's this paper by Leonid and Bufatov where they kind of formally write down this kind of a definition, and they don't call it a probabilistic bijection, they call it a bijectivization. But I kind of, yeah, we just decided to call it a probabilistic bijection. Okay. So, right, okay, yeah, so there's been a lot of work in the past 10 years on single parameter randomized insertion algorithms. So these are related not to the Macdonald polynomials, but to either the Q-Whittaker or the Hall-Littlewood polynomials.
I'm sorry. I think qRSt column is also in my work with Matveyev, right? Or not?
Yeah, I probably should
that?
have put that there here. Yeah, it's so. Yeah, I should have put that there.
Okay.
Strictly speaking,
it's good that you agree because I wasn't sure, but.
I mean, so I would say, strictly speaking, that the algorithm you give there is. So I guess what we're trying to, what we're looking for, kind of, or at least what the difference between that one and all the other cases is that you can't choose it. You can't have your input be deterministic for that column qRSk. Do you agree with that?
I think we can.
Oh,
we were looking for dynamics that kind of propagate all the way, use the least amount of randomness.
okay,
and
well,
I'll have
maybe
to look at that again, but I'm pretty sure we can. In all our 4 algorithms in that paper, I'm pretty sure we have deterministic inputs.
Yeah.
Okay, maybe we should talk about that, because I looked at the column one, and it seemed like I couldn't figure out how to separate out the randomness of the input. But maybe
Right, let me take
just
a look again. I'll take a look. I'll probably before the end of the talk can get back
and
to
I mean,
discussion.
so that's not to say it's still a very nice algorithm. I guess I didn't include it here because it didn't quite fit into the framework I was talking about, but I'll in my next version of this talk, I will mention it.
Thank you.
We do mention that in our paper. Although I think not in the version of the paper that's currently on the archive. So the version that will be on the archive soon, we'll have a remark about that. Okay, and so these algorithms. Maybe I should say what this means. So if you're not familiar with this, so what this row and column means is that so the Robinson Schensted algorithm that I described before was the row version. So I try to stick things in the first row, and then if something gets bumped, it moves up to the next row. But you can also think of kind of inserting from the left. So you can try to put something in the first column, and if it needs to bump something, then that thing goes to the next column. So there's these two kind of, dual versions of the algorithm. And when you start trying to do these deformations, so you can try to do a q deform, you can try to do a deformation of the row version or a deformation of the column version. So it might be worthwhile to just go back here for a second and do an example. Is it possible for me to annotate? Well, I don't see how to annotate in here. Maybe if I go here. All right. Well, I guess I'll just try to say what I mean. So, if you take this example and you set t equals 0, what happens is this probability gets killed. So, at t equals 0, this permutation has to map to this pair. Whereas this permutation maps up here with probability q and over here with probability 1 minus q. So the way that you can think about that is that it's defining an insertion algorithm where when you try to put a new number in, the new number always goes into the first row. But then if something gets bumped, it has a choice of staying in the row or bumping up to the next row. So that's why, so when I insert first 1 and then 2, there's no bumping, just the 2 sits next to the 1. But when I insert the 2 first and then the 1 bumps the 2, and then the 2 has a choice of whether to go up or to the right. So in general, there's this qRS row algorithm of Borodin and Petrov works like that, where things that get bumped can either, so you always insert into the first row, but then if something gets bumped, it can either stay in that row or move up to the next row. And the column one is a little different, actually. You try to insert things from the left, but you kind of actually have a probability of inserting it anywhere. It doesn't always go into the first column. And then there's various different variations on these algorithms, and there's some generalizations to the full RSK setting of semi-standard Tableau. So, right, and anyway, so these algorithms they arose in the study of Macdonald processes, and they were used to analyze a variety of integrable models like the ASEP and the stochastic 6-vertex model and several others. And the fundamental idea in these applications is that you can view a semi-standard Tableau as an interlacing array of particles. So a sort of a nice exposition of this is this paper by Borodin and Petrov. The paper by Matveyev and Petrov has a very nice exposition of how this works. Kind of a sort of high level view is that what happens is if you kind of look at this interlacing array of particles, and you kind of take like the leftmost particles under one of these algorithms. I think it's like maybe the column version. If you take the leftmost particles, this is actually the evolution of the TASEP, or of the q-TASEP. So somehow by looking at these projections of this process onto just a piece of the Tableau, like the first row or the leftmost column, you actually get the dynamics of these various systems, and then you can use the power of the Macdonald processes and the Cauchy identity to analyze those systems. Okay. So any questions?
Okay, yeah. So Gabriel, I'm pretty sure what I said is right. So we have an RSK, meaning that there is an input. So I put this in the chat, like the precise reference. There is an input, which is a random q-geometric random variable, but you can fix it, and then this is your input, is an integer. And then something happens, which is strange and random, but that's the randomized insertion.
Okay, I think I'll have to think about this again, but I may have to. Yeah.
All right. Yeah, of course.
I'll take another look at it. Yeah, maybe I misinterpreted what you were doing. Okay.
Yeah, we should continue this discussion.
Yeah, definitely.
Okay. Sorry.
Yeah. Okay. Okay. So now, so my goal basically for the remainder of the talk is to explain kind of where these probabilities come from and how we generalize them for any permutation. So I want to kind of take a step back and think about what exactly is an insertion algorithm. So, okay, so one way to think about it is to use these up and down operators on the lattice of partitions, Young's lattice. So the up and down operators are linear operators where the up operator, so I'm working with this vector space spanned by, so it's got a basis indexed by all the partitions. And then I define this up linear operator, which sends a partition to the sum of all the partitions that can be obtained by adding a single box. And then the down operator sends lambda to the sum of all the partitions that can be obtained by removing a single box. So the key property of these two operators is that they satisfy this commutation relation. du minus ud is equal to the identity. So what this relation, it's saying two things. It's saying that if I pick two different partitions, lambda and rho, that the number of ways to go up from lambda and down to rho is equal to the number of ways to go down from lambda and then up to rho. And the other part of the relation is saying that if I just have a single partition lambda, the number of ways to go up and then back to lambda is one more than the number of ways of going down and then back up. So the number of boxes that you can add is exactly one more than the number of boxes you can remove. So this is not hard to see. So if you have two different partitions, it's easy to see that there's either exactly one thing above and below them both or nothing. So these sets are both either singletons or empty. This relation is more interesting because these sets can be, big in general. And it's sort of, if you just kind of look at an example, you can kind of convince yourself pretty easily that the number of outer corners, which are these blue ones, is one more than the number of inner corners. But it's useful actually to take an explicit family of bijections. So for each partition lambda, I want to fix a bijection from the red boxes to the blue boxes. But of course, there will always be one blue box left over. So what I do is I kind of extend this set of, I kind of, over here I take the box, I take the set of bigger partitions, and over here I take the set of smaller partitions, plus I include the partition lambda itself as this kind of +1. So there's, of course, there's infinitely many different families of bijections, but there's kind of two natural ones. One of them is to send an inner corner to the outer corner in the next row and view this as the leftover one. And the other thing is to send a box to an inner corner to the outer corner in the next column and view the one in the first column as being the extra one associated to lambda. So, right, so what's kind of cool is that every choice of a family of bijections like this for all partitions lambda gives rise to a deterministic insertion algorithm for inserting a permutation to a pair of tableaux. And the idea is that f lambda of lambda, so the box that doesn't have anything pointing to it, that's what you do if you're trying to insert a new number. And then these arrows tell you what to do if something gets bumped. So if I tried to insert a new number and then there was something bigger there that had to get bumped, these arrows would tell me where I should move it to. So it kind of, if you think a little bit about it, you can see that this bijection is sort of precisely describing row insertion. I'm kind of leaving out a little bit of the details of how this works, but basically the idea with row insertion is that new things come into the first row, and then when something gets bumped, it goes up to the next row. Column insertion, new things go into the first row, and then when something gets bumped, it moves over to the subsequent column. And really the best way to understand this is with Fomin's growth diagram. So this is what we do in our paper. We explain how all this works, but I don't have time to do that here, unfortunately. Okay, so what we want to do is we want to take this up and down idea and these local bijections and generalize it to Macdonald polynomials. So what we do is we define Q and T analogs of the up and down operators by, instead of just taking the sum over all bigger partitions, you have to weight them by this weight, which is coming from the Macdonald, the weights in the Macdonald polynomials. And there's these weights that come from the P lambda and the weights that come from the Q lambda. So in this case, the key relation is almost the same, but you have this extra factor of 1 minus T over 1 minus Q. Again, this boils down to two things. There's a thing about if you take two different partitions, then there's that one thing in between, and it's sort of not too hard to show that the weights of going like this are equal to the weights of going like this. But the non-trivial assertion is that if you start with lambda and you sum up over all the ways of going up and back down, this is equal to the number of ways of going down and back up, plus this extra factor. So what we wanted to do was find a family of probabilistic bijections from the things on this side, so the smaller partitions plus lambda itself, to the bigger partitions, and we wanted to find a probabilistic bijection between these two sets. And the idea is that such a probabilistic bijection gives rise to a randomized insertion algorithm, where when you want to put something new in, that's when you use you consider this case. So you say, what's the probability of just adding a new box to get a certain outer corner? And if you're trying to do bumping, then you kind of say, what square was it bumped out of? And there's various probabilities of where it will end up. So I'm kind of brushing some of the details under the rug, but that's kind of the idea, is that you just need to define these probabilities. So what this does is so in the 2x2 case, it was kind of not hard to just stare at it and come up with nice probabilities. But in general, it seems sort of intractable to, come up with a way of mapping n factorial things to n factorial things. So instead, we break it down into these smaller steps of just kind of adding one box at a time. And then the bigger probabilities in this big picture just come from kind of applying this randomized algorithm in sort of all the different ways that it can play out. Okay, so now the final part of the talk is actually explaining what these probabilities are. So if we think back to the hook walk from the beginning, that gave us a random way to add a box to a young tableau, to a young diagram. So that's kind of what these initial insertion probabilities are. So we want to sort of say, if we have a tableau and we want to put a new number into it, where does it go? And it turns out that what we want to do is do a QT generalization of the hook walk. So it's the same idea as the original hook walk, where you start with a box that's beyond the rightmost column and above the topmost row. But now you don't choose a box in the red uniformly at random. You weight it. So you move j steps down with this probability and I steps to the left with this probability. So you can check. It's not too hard to see that this does in fact define all these things sum up to 1. And I guess so. A here, yeah, right. A is representing this length, and L is representing this length. So so Garcia and Heyman had a similar construction taking place inside the Young diagram, and that sort of inspired this definition. Okay, so the reason why this is a good definition is because the probability of reaching a certain outer corner is very nice, like in the hook walk case. So what we need it. So in the normal hook walk case, the probabilities were these ratios h lambda over h nu. So what we want here is a qt analog of that ratio. So it turns out that the right thing to do is this quantity alpha nu over lambda. So the basic idea is you look at all the cells that are in the same row as nu over lambda and all the cells that are in the same column. And for each of those cells, you take the ratio of a qt deformation. So the point is that there's kind of two natural ways that you can qtify the hook length. You do q to the arm and t to the leg, but then there's the question of where does that extra one for the box itself go? Does it go into the leg or into the arm? So, well, neither one is better than the other. So it turns out what you do is you say that if the cell was in the same row, then we're going to put that extra one into the leg. If it was in the same column, we're going to put that extra one into the arm. This is this thing, and it's sort of, it's clear that if you set q and t equal to 1, you just get the ratio of the hook length. So the point there is that if I set q and t equal to 1, then what happens is each of these factors just becomes the hook length of lambda divided by the hook length of nu. And then I'm not doing all the boxes. I'm only doing the boxes in these row and column, in these rows, in this row and this column. But if I take a box that's not in one of those rows or columns, then the hook length with respect to nu is the same as the hook length with respect to lambda. So all of those things are just going to cancel out from this ratio. Okay, so the result that we proved, one of the results is that the probability that you reach a certain outer corner using this qt hook walk is independent of the starting box in the same sense as before. And it's equal to a power of t times this quantity here. So one thing you can see is that if t is equal to 0, then the only way this will be non-zero is if the box is in the first row. And so this corresponds to that Borodin-Petrov algorithm. In fact, it is the Borodin-Petrov algorithm where you always add things to the first row. Sorry. Okay. Right. Okay. So now, can I go, if I go till like 11:15, is that okay?
I think the talk is very enjoyable, so you can go on.
Okay. Thank you. Okay. Right. So, right. So there were these two things we had to do. We had to define the probability for adding a new box, and then we also have to define bumping probabilities. So the bumping probabilities are more complicated, and we don't really have as good of an understanding of them. But it turns out that what we want to do is define a qt analog of this quantity. So this is the probability that if you bump something out of lambda, so if you had your tableau of shape lambda, and then you end up trying to bump something out of mu, what's the probability that it's going to land in that box? So it depends on lambda and mu and nu. So somehow what we end up wanting to do is take this ratio of hook length products, but then we also have to divide by the square of the hook length of this cell that's in the intersection of the row and column of those boxes. So precisely this is the definition. So you take a ratio of these alpha quantities, and then you have to throw in some other factors with these various exponents. But I just like to think of it as just being an analog of this. And then we proved that if you fix mu and you sum over all the nu of this quantity, you do in fact get 1. So okay, well, so one thing you might be wondering is where did this thing come from? How did we even come up with this? Like, there's no hook walk in this case that could have motivated us, and I'll explain that in a slide or two. Another thing you might wonder or one thing I wonder is why do these things sum up to 1? Even in this q equals t goes to 1 limit, why do these expressions sum up to 1? And so the only answer I have is that we proved it. And the way we proved it was we sort of wrote down very kind of, we wrote down certain, we figured out that we could express this thing as a certain algebraic formula, and then we used Lagrange interpolation to prove that they sum to 1. But I would very much like to understand, either combinatorially or by some probabilistic mechanism, like some sort of hook walk maybe, why, like where do these things come from? Why are they probabilities? I have no idea. Yeah, so one thing that would be really cool, although I don't know, and this might be too much to hope for, is there some sort of generalization of the hook walk that somehow takes into account this square mu and ends up in the square nu with exactly this probability. I don't know. Okay, so I want to just kind of explain where we came up with these probabilities, especially given that we don't have a nice procedure like the hook walk for the bumping ones. So our goal was to prove this identity. And we wanted to find a probabilistic bijection. So we used this lemma, which I learned of actually from a talk by Leonid at the JMM last year. Here's the idea. So what we wanted to do is we wanted to define probabilities satisfying this property. But the trick is that this holds if and only if you can define backward probabilities that also sum to 1 and are compatible with the weights in this sense. So I kind of like to think of this as this is the inverse of the probabilistic bijection. So, you know, if in the deterministic setting, if you have a map and you want to prove that it's a bijection, often the best way to do that is to explicitly write down the inverse and check that it undoes your first map. So this is kind of the same idea, is that the best way to prove that we have a probabilistic bijection is to explicitly write down the inverse and show that this is the equivalent of the showing that they undo each other. This is the condition that needs to be satisfied. So this lemma is trivial to prove, but thinking of it was, I didn't think of it until I saw a slide that looked a lot like this appear in one of Leonid's talks. Right, okay, so now, and this also ends up being our secret. So we wanted to prove this identity, and we looked at the explicit formulas for these weights, which looked something like this. They're just ratios of these two different analogs of hook lengths. So what we did is we just kind of stared at these, and we defined our probabilities by kind of splitting. We took kind of half the terms from here and half the terms from here and put them into the forward probabilities, and then took the other terms and put them into the backward probabilities, so that automatically these relations were satisfied. And then what was left to do was to show that these expressions that we defined actually were probabilities. And we did that using Lagrange interpolation. And then after the fact, we sort of looked at these probabilities and realized that they were related to this hook walk. And but that I sort of told the story in reverse. We didn't start with the hook walk. We started with these formulas, and then turned out that they could be thought of as coming from a QT hook walk in this case. But in this case, they're a little bit more mysterious. Okay, so, okay, I think I just have 2 more slides left. So, right, so here's kind of a picture of the various specializations. So, so qRSt is something about Macdonald polynomials. If you set t equals 0, you get this Borodin-Petrov algorithm, which was generalized to RSK by Matveyev and Petrov. At q equals 0, you get some sort of t row insertion. I think that wasn't explicitly studied, but it's sort of similar to another one. And then if you set both of the q and t to 0, you get regular row insertion. On the other hand, if you invert the parameters, so if you invert t and q and then send t to infinity, you get a column insertion version of Robinson Schensted, a q version of that, which was discovered by O'Connell and Pei. And if you do this inversion and then kill q, you get a t Robinson Schensted column version, which was due to Bufatov and Petrov and generalized to RSK by Bufatov and Matveyev. And so I think what Leonid is saying is that I should also have Matveyev Petrov in brackets here. And then if you send q and t, if you kill both of them after inverting them, you get column insertion, which just has to do with the Cauchy identity for Schur polynomials. But then we also have this other thing we can do, which is to set q equal to t. And if we set q equal to t, then we reduce to Schur polynomials. So in that case, our algorithm is giving sort of a whole family of algorithms that sample from the Plancherel measure that depend on this single parameter q. And from that, if we send q to 0, we get deterministic row insertion. If we send q to infinity, we get deterministic column insertion. And if we send q to 1, we get this kind of strange uniform sampling property that I'll discuss now. So, right, so it sort of follows from everything I've been saying that the Plancherel measure can be sampled by applying the q equals t specialization to a uniformly random permutation. But if we think back to the beginning of the talk, the 2 sampling algorithms from there have a stronger property that not only does the shape lambda appear with the Plancherel probability, but each tableau of shape lambda appears with probability f lambda over n factorial. So this is stronger than just sampling the shape with a certain probability. Now, this stronger property does not hold for the q equals t specialization in general, but in the limit as q equals t goes to 1, it does hold. So if I take any permutation and insert it using this algorithm, and I just look at the insertion tableau, I don't look at the recording tableau, then the probability that I get a specific tableau of shape lambda is f lambda over n factorial. So it's independent of the tableau and independent of the permutation. So it's kind of, it's sort of easy to see this if you start with the identity permutation. Because if you start with the identity permutation, you're just always doing the hook walk. You first put in 1, then you put in 2, then you put in 3, there's no bumping. But if you take a different permutation, then you have some hook walk steps, but you also have some bumping. And somehow the bumping works out so that you still get this same probability of getting any tableau. So we thought that was kind of curious. Okay, and then there's, so here are some questions that I think maybe I hope people in this audience might have some answers to these. So there's this question of trying to extend to RSK. And so, you know, so the dream, the hope is that there is a q-TRSK which specializes to like the qRSK. So there's these two qRSKs that Matveyev and Petrov have, and there's this t-RSK that Bufatov and Matveyev found. And so ideally, you know, is there some master RSK algorithm that specializes to all of these things? I don't know. I'm not sure if I really, I'm not sure I think that there is. There might be, but it's not so easy to find. Although it is straightforward to do it in the case of just words rather than arbitrary matrices. So such a thing does exist in the case of words. And then I have these sort of these questions like, so are there integrable models depending on two parameters that could be studied with qRSt? So one difficulty is that you don't have these nice Markov projections to the first several rows or columns, because the bumping step, it's sort of like in the t=0 case, you kind of always move things up. But in our case, you put something in anywhere. When something gets bumped, it can go anywhere. So you kind of, if you want to know what's happening in the first row, you have to understand what's happening everywhere, not just what's happening in the first row. So I don't know about this. And then, yeah, I'm wondering if there might be like a qt polymer. Although I'm not even sure if there's a q polymer or a t polymer. So yeah, I'd be interested to know if any of you have thoughts about these questions. So thank you for listening.
So have you thought about taking the jack limit of your
I'm sorry?
Have you thought about taking the jack limit?
The jack limit. We haven't looked at that. Yeah, yeah, that might be interesting to do, but we are there probabilistic models associated with the jack limit?
Random matrix models.
Oh, really?
Beta ensembles.
Oh, I didn't know that. That's interesting. Do you
Question
have?
is, can you get from Plancherel, Jack Plancherel to matrix beta? But there are works about beta Plancherel by Alex Moll.
Let me write this up. By Alex.
Let me find.
I mean, I suspect that the QT hook walk, I suspect that if you take the jack limit and apply it to the identity permutation, you probably get some sort of jack Plancherel. Although I don't, yeah, I haven't really thought about that.
So do you have a sense where the QT hook walk, or even where the regular hook walk comes from? Like with a lot of things with Schur polynomials, you know, we say, oh, you know, this is the branching rule for unitary groups, or, you know, this is something, or this is something. Is there anything like that for the hook walk?
Not that I know of. Yeah, I don't know of. Well, I mean, so the identity that the hook walk is proving is this Cauchy identity, or if you just look at a single step, it's proving this upper recursion, which says like the number of it basically a single step of the hook walk is kind of proving something like the Pierre rule or something, something related to the Pierre rule, but the hook walk itself, I don't know of any representation theoretic meaning for it. It's just kind of this miraculous thing that these guys came up with. I don't have a better explanation for it than that.
Can I comment on the polymers too? So there is a paper by Pei that has a q-polymer in the title. But
that's a good point.
But it's not a but that's kind of a pretend polymer. Most like it's a random recursion solution to a random recursion, which is not a polymer in any way. Like there is no environment that you can define a polymer in.
Oh, huh.
But there is a random recursion for the qRSt that he's calling q-polymer.
Oh, okay, I should probably.
I personally don't agree with the name, but that's fine.
Okay. Or I guess another thing that I was wondering about. So if you take like the q goes to 1, there's sort of this like tropical limit of the qRSt that gives you the usual polymer, right?
Yeah.
Is there any way that you could? Is there any sort of like T polymer that you might get by like? So like, I guess in our case, it would be you do some sort of tropical limit with the q, and then you still have a t. And do you know of anything like that?
No.
Simply setting q equal to 1 here does not, the system does not scale.
Right. And I guess actually, so probably you would need to have the full RSK version, because like the polymer thing doesn't really make sense. Like you sort of need to have matrices for that, if I understand correctly. There's kind of no like permutation version of that. So we might need to have the q-TRSK to even be able to think about that.
Have you done that?